So with that,
Mhm.
just in general, because I don't want to ask about Wilson specifically, but is it like different racket products are sold to different user groups? Like one racket might be more geared towards professionals, and then another might be more geared towards beginner
Yeah,
level or middle school, high school level.
100%. It's really cool because like beginner levels, people mainly buy rackets for their looks, so design's more important. Whereas professional, they really don't care about design. They care about how it performs. So a lot of the innovation that I'm talking about is directly to these.
Hello, everyone. Welcome back to the It's a Material World podcast. I'm your co-host Puneeth. Joining me today is my co-host David. David, it's been a little while, so what's new?
Yeah, I've been a traveling man, so I've been in Texas for the past few weeks. So finally back home now and about to go on vacation back to the
Yeah,
East Coast for Christmas and the holidays. So
yeah,
super excited to take a break. What about you?
yeah. And we'll get, I'm going back home soon, so I think we'll be able to see each other in person for the first time in a little while. What has it been? Has it been since Barcelona?
Yeah, Barcelona. So
Oh my
a
gosh.
year and a half.
That's crazy. Yeah, that's insane. I feel like I see you all the time, but it's just over a Zoom call. But yeah, work has been busy. Usually I feel like it's less busy near the holidays, but it really ramps up this time for a number of reasons. But that's kind of, calmed down a little bit as we
Yes.
get into the break. But yeah, super excited to talk about this podcast episode. We brought on Koki Asahina, who is an intern at Wilson and specifically works with their rackets, tennis, pickleball, etc. And it was just a really fun conversation to, you know, you and I are avid sports enthusiasts. Any sport can be interesting, and he was the same way. So it was really cool to see how his material science background, and he even has kind of a little more of a unique background where he has a minor in physiology as well. So it was just really cool to see all of that intersecting with the sports industry. And I wanted to see if you had any favorites from the podcast episode that you wanted to touch on.
Yeah, he focuses on tennis, which unfortunately is probably my worst sport. So I wasn't able to relate too much, but no, it was really interesting hearing about their product design cycle and how it really is just like these slight tweaks can mean the world of difference to these athletes and getting feedback from all levels to make an informed decision on how to roll out products, how to roll out products to different groups, and how to be like an effective like take a subjective opinion and create an objective manner to analyze these rackets to understand which combination is the best. So I thought him walking us through how he dove into all these different aspects was really fascinating for the product development cycle.
Yeah, I couldn't agree more. And just on top of that, we also touched on physical testing versus simulation and how you kind of balance the two, right? And where, especially in this day and age with software up and coming, it can be easy to be like, just really put all of your eggs in the simulation basket because it can accelerate R&D timelines, et cetera. But he was talking about, and he did a really cool comparison of, the sports industry and, relatively cheap products to kind of that can fail compared to maybe the aerospace industry, right? And how this is more conducive to allowing for that physical testing and putting a lot more weight into that and finding the balance between the two. So it's just really cool hearing about his experiences and his advice too for other engineers who might want to get involved in this space. So there's a lot to touch on. Really fun episode. And yeah, without further ado, let's get into the episode.
All right, hello everyone. For today's episode, I'm excited to introduce Koki Asahina, a racket sports engineering intern at Wilson Sporting Goods Company and a fourth-year MSc student at Georgia Tech who also has a minor in physiology. His other internship experiences include Caterpillar Inc. and a research experience at the university's Human Neuromuscular Physiology Laboratory. Kokia, welcome to our show. It's a pleasure to have you on.
It's a pleasure to be on. Thank you guys so much for inviting me.
Yeah, thanks, Koki. I'm looking forward to it. Just as I remember walking out along Millennium Park yesterday, and there was like a Wilson, the
Oh
Wilson
yeah.
building is right next to it. So
Mhm.
I was like, oh, cool. We're interviewing someone who's interning there. So
I was probably there yesterday, right as you walked by.
oh yeah. Awesome.
Yeah.
So I know for David and I, we love sports. We talk about it all the time. So the intersection between sports and engineering is definitely fascinating for us and potentially, our audience as well. So just wanted to get your background and understand what drove you to pursue an internship experience kind of in this sports industry. And also, why you chose physiology as a minor to accompany your MSc degree.
Yeah, of course. So, like you said, I'm a enthusiast like the two of you are. I was personally a competitive swimmer for elementary, middle, high, and the first year of college as well. So, when it came to pursuing something, I wanted to stay in the sports field, hopefully, and wanted to an interest in a career that related to sports. Now, I was more a mathematics mind than I was a humanities mind. So, it was only natural that I wanted to apply some sort of mathematics to the sports field. And the solution to that I came up in was sports equipment and being able to apply an engineering to help athletes like we were or enthusiasts like we are perform better in their sports. Now, physiology, why that is a logical approach to sports equipment. So you can approach the two words sports equipment. You can approach from the word equipment, which would be the engineering, the mechanical engineering, material science, the engineering side of trying to develop tools. And then you could go from the sports side, which would be understanding the human side, biology, biomedical engineering, physiology. And so combining those two is the reason I did material science and physiology.
Yeah, so physiology is like very popular for people who go into the medical field, but I feel like not as like exposed or focused on for engineers. I guess how have you first found yourself so interested in physiology? And then second, do you find other people that can help you along your journey or with similar passions in this more engineering type focused school?
Yeah, yeah. Without doubt, Georgia Tech is super engineering focused. And so a lot of mathematics, a lot of creation. Physiology is cool because I mean, we all have bodies and we all want to know how we move. So being able to understand and study that really kind of cool. The way I meet people who are like-minded, I is very centric to the my experience at the Human Neuromuscular Physiology Laboratory. I'm an undergrad researcher for them, and I'm working on creating a new method of Parkinson's rehabilitation by stimulating a certain nerve going down your spine. And so that experience, I think, is really key for me to meet people who pursue this biomedical engineering or like physiology or biology as their main core focus. For us, obviously, it's material science, but these people have that as their main priority. And they know so much more than we do. So being able to mingle, hang around the PhDs, the professors, and the graduate students who do that gets you a lot more how accustomed to their language, accustomed to their way of thinking and their expertise to, get the broad information background that you're trying to seek.
That's awesome. So I'm curious, are you able to leverage your within this neuromuscular physiology laboratory, how are you able to leverage your material science background? Because, in a similar fashion, I find in the medical device industry, there's a lot more BAs, biomedical engineers, obviously, and then, probably next is mechanical engineers. There's few and
Yeah.
far between MSEs, but now I've become kind of that materials SME to a certain extent within our group, within our R&D group. So I just wanted to ask if that kind of same principle translates within the physiology laboratory for you.
Yes, spot on. So, I mean, if you want to study the human body, you need tools to study the human body. And many times that's like selecting correct materials. If we go back to that neuromuscular lab, if we want to stimulate a certain nerve, we need something that stimulates that certain nerve. So that could be conductive material that sends electricity through that nerve or insulating it to not electrocute yourself or, adhesive material like elastomers to adhere such sensors to your body, that kind of thing. So I think it's very much intertwined, material science and physiology. One complements the other and helps each other out. I think more broadly, if we're going, the thought processes are also very similar. You say that engineers are primarily here, but I think physiology also thinks in the same way. Like if we take this pencil and we snap it, we know it's going to snap. But our material science is their job is to be that detective that figures out how it snaps and why it snaps and doesn't plastically deform, if that makes sense. And use that knowledge to maybe make a pencil that does something different. Physiology is the same way. You don't think about how you walk day to day, if that makes sense. So our job is to take what we do so naturally and then reverse engineer it and understand why we do the things we do so well. And then if there's someone like with Parkinson's who can't walk as well as we do, how we can use our knowledge to help them. So the thought processes are very, very paralleled. And both fields are growing. Material science, especially, seriously a growing field. So I think our applications and our uses are gonna only grow.
Can you give potentially an example of how material science innovations in particular can serve for those like physiology based needs like you were talking about Parkinson's rehab research? Maybe you can share an example there of that specific material science innovation or even a possibility of it, or if you're maybe not allowed to talk about that, maybe in general in physiology lab research how material science can provide that innovation or that infuse that kind of
Yeah,
innovation into the space.
100%. I mean, you can approach it from two ways. You can go from outside. So you can either have a material that goes on the surface of your body, or you can have a material that goes inside your body. And so I think our understanding of biomedical engineering very much is skewed towards the inside of the body. But the materials I work on, I don't go invasive. So a lot of it's going to be, as I mentioned, conductive gold material to send electric pulses through just a small, really small pulse of electricity through a certain vein or a certain nerve in your body, that kind of thing. But coating it with insulating material to not send not distribute electricity to places you don't want it to be. And of course, if we go apparel or clothes or equipment, all of that is again tools that serve the physiological needs of an athlete, even if it's not rehabilitation specifically. And the engineering goes hand in hand. And those are all of these are big brands that take men. So the world's abundant with examples like that.
So maybe we can dive into one of the brands that you were working for with a Wilson R&D project. I'm really curious for applications that are more like consumer. He said we can reverse engineer how we walk, how we use the materials, but for more general approaches like consumer goods, how do you work on a project from start to finish? And how does the material science work for the first half? So maybe can you talk about how materials performance data plays a crucial role in the initial testing and how you kind of define a spec for whatever product you're using?
Yeah, for sure. So Wilson, for them, I created a simulative tester that basically tests and deepens our understanding of how a tennis racket reacts to hitting a ball. So I was in the tennis development team. So we're talking tennis rackets, pickleball rackets, padel rackets, badminton rackets, racquetball rackets. All of these rackets Wilson is quite dominant in, as we probably both know. And so my task was helping them innovate. So when it comes to Wilson R&D specifically and how material science comes into play, it's a very much a rapid prototyping process. So Wilson benefits in that if you have raw material, you can bladder mold it into a racket frame. You can string it, you can grip it, and you can play with it on our facility tennis court on the same day, which is unique to my knowledge. And so when you have a new idea, when you have a new material that you want to test, it's very, very easy to just stick it in a racket and go play with it. And that's a good benefit. My project fits into this because it's one of those machines that's going to test tennis rackets on the spot and rapidly prototype. Now, I think that's not something you can do with every industry, obviously, because I mean, airplanes or rockets, you can't just make one and break one. Lives are at stakes. So tennis rackets, and I think the greater sports industry really benefits from this because ultimately it is just a toy. Like if you break a tennis racket, yes, it's expensive, but like it's not catastrophic. You can just get a new one. And so this rapid prototype, trial and error, if new materials come along, to just literally stick it in before you try anything else is very beneficial. And I think, unique to the sports industry and fun because you can see your ideas flourish in real time instead of, decades for it to come to a product.
For sure. I am wondering if you can go a little bit more in detail about why it's so important to get that user feedback and for, you as an intern, other engineers to use these rackets or, whether it's in a prototype phase or just it's already commercial and requires improvements. I don't know. I just would love to hear kind of at that point, Wilson is a very established company, love their rackets, right? So what kind of changes can you make and how do you feel that, when it's already such an established product?
Yeah, so you hit jackpot on feel. So unfortunately, we are super subjective as people, right? So an equipment that you pick up might not be the same feel that I pick up. So, and it's not very quantifiable. In material science, a lot of the applications we try to work for is very objective. So we're measuring ultimate tensile strength, yield strength, Young's modulus, that kind of thing. Very quantifiable data points. But even if we have the best material specification wise, if it doesn't feel good to the athlete, there's no point using it. Many times the worst materials might actually feel the best to the athlete. And so if we go about engineering a solution, it's understanding how having athletes, whether it be employees, whether it be beginner level players, whether it be professional players, fill out these forms and give subjective feedback. And it's our job to try and correlate trends, change one material spec, see how the athlete likes or doesn't like it. Many times it's a case of I talk to athletes, it's what does wobble mean? What does stiff mean? What does too flexible mean? What's bending? Like, and trying to translate all these subjective words into quantifiable variables and trying to interpolate a single solution to it. And so I don't know, it's beneficial to have a sports background for sure, because I mean, if you are an athlete, you use these words on a daily basis. Oh, this is too tight, that's too loose, kind of thing. And so being able to try the rackets that we make ourselves and then iterating that final product to help the consumer first, obviously, more so than the specification and the data sheets. It's
So you're talking about the subjective feedback, but I feel like many times if I was asked for subjective feedback and like I'd have a strong opinion, they would all kind of blend together. I guess how do you set up a proper experiment where there is enough difference to be able to tell? And how do you avoid just everything kind of being all threes instead of actually seeing some variance within the response?
Yeah, so first is the products and the samples you provide to these people. So we have what is called a vanilla. A vanilla is a standard, bog standard, nothing changed racket. What's on the shops in the stores right now, because that's good, right? And then if we have that sample, and then we have a new sample that maybe uses a new material or changes geometry, changes a tiny little one variable of it, basically. And so we give both of these rackets to player. We don't tell them which one's which, and we tell them which one do you like more. And then we have like forms that tell us, stiff, not too stiff, bounce, like plow through, not good, shots aren't going into the court, that kind of thing. These kind of metrics for us to measure that are standard for every single racket test that we do. And when you do that, and when you do that specifically for people all the way from the beginner level all the way to ATP professionals, you get this broad spectrum of feedback. Obviously, beginners aren't going to be able to feel as much difference as professional players, but that's good because a lot of the times the product you're making for is for one professional and a whole host of consumers. So getting that balance right, getting these very objective ways of measuring subjective feedback is very important. And I think that's something Wilson's very, very good at.
That was a great point that I actually wanted to ask about is those different user groups, right? You talked about, maybe how a beginner, their sensitivity would be vastly different than a professional. And then there's so
Yeah.
much in between, like my brother playing tennis in
Mm-hmm.
high school. So with that,
Mm-hmm.
just in general, because I don't want to ask about Wilson specifically, but is it like different racket products are sold to different user groups? Like one racket might be more geared towards professionals, and then another might be more geared towards beginner
Yeah.
level or middle school, high school level.
100%. It's really cool because like beginner levels, people mainly buy rackets for their looks. So design's more important. Whereas professional, they really don't care about design. They care about how it performs. So a lot of the innovation that I'm talking about is directly to these performance rackets. that professionals use. So there's 5 franchises at Wilson, and all of the players on the court use one of these 5 franchises. And when we want to test new innovative equipment, we apply them to these 5 franchises because we know that performance is going to help these people who can actually exploit the new technology that we give them. But once it's a top-down process, once you have it on that top level tier and they appreciate it, then it's consumers, like if you have Roger Federer, the tennis player, is using this racket, we all want to use the same racket that he does because he's awesome and he's the best in the world and whatnot, whatnot. And so this technology then gradually trickles down into the consumer market, eventually becoming the norm. And then it's a cycle of that. Try a new thing, trickle down, try a new thing, trickle down. And one more point that's important is that for consumers, price is really key. I mean, professional athletes, they're sponsored, so they don't pay, or more like they just pay a bucket load of money for however many rackets they get. So it's a lot of many times the new material might not be feasible in terms of cost for a consumer, or you might need to get economies of scale before it's implementable into an average, $30 Walmart racket. And so, there's different teams that work on this at Wilson and try and navigate the different consumer and markets that each of these rackets.
So when we talk about like innovation or product design, a common adage is like fail fast. Basically, it's
Mhm.
better to know that something doesn't work faster than waste more time. How can you embrace that through your experience, and what can you take away from like failing while still learning a lot at the same time?
Yeah, I definitely think the biggest takeaway from Wilson's internship and the way they go about things is to not be afraid to try new things. Most of what I did during this internship for that simulative tester I'm talking about, it's computer programming, mechanical engineering, and electrical engineering. While I did a lot of material science in other projects, for this project specifically, it was a lot of things that they don't teach you at school. But I think the biggest thing school does teach you is how to learn, in that how to identify the things you need to know, how to absorb information really, really quickly and apply it on the spot. So our rigorous programs that Georgia Tech has, or the clubs that we do, aim to bolster this more so than the actual content. In my head, this is my belief, what the Georgia Tech helps us do in that sense. And it really gives us, Wilson has given me a sense of that innovation doesn't happen on its own. You need to keep working on it or else it becomes stagnant. And this fail and try new attitude is really important, not just in the sports field, not just at Wilson, but other fields as well, to keep pushing the boundaries, even if initially it's not your field, even if initially it's not something you've learned or something you've tried. Most of the things you try at work aren't things you've ever tried. Or many times they're things that no one's ever tried. It's an industry first, that kind of thing. And so being able to continue pushing is I think the spirit of an athlete, first of all, but also the spirit of an engineer. And failures come as a result of that, and that's totally fine.
I love that. So Koki, when you talked about the kind of rapid prototype cycle within Wilson and how, you can have, you can manufacture these prototypes and then potentially use it like same day or next day as an engineer. So what kind of things do you get like provide feedback on as the engineer if you go out on these courts and you use these products that then lead to potentially sending them to the next kind of phase of user groups, like an athlete, right? Like I'm just curious what you can bring to the table with your engineering background, and maybe are you just kind of like a screen, like, oh, that just did not feel right at all, like there's no need to even send that to an athlete, we just got to try something else. What exactly are you providing there?
Yeah, so we play tennis. Most of us play tennis. And so, or at least at Wilson. So I'm in the unique position, and a lot of the Wilson employees are in the unique position in that we do the sport and we understand the sport technically. So this won't be the case for professional athletes where you play a tennis racket and you feel stiffness, and in your head you see the carbon fiber and what it's doing and understand, or at least have an inference on the spot to why you feel the things you do. Now, professional athletes, all they do is not all they do, I mean, they are the best in the world, but they feel a difference in the tennis racket, but they don't have a connection to that engineering base on why it's doing that. So their feedback is very, very valuable, but it is simply consumer feedback in the blind, if that makes sense. Engineers who play tests are able to, if I bring back feedback to someone like an engineer, another person on my team, many times it's a case of, oh, this is what I feel. Sometimes it's, yeah, wow, this is terrible. Don't even try. Or sometimes it's, this is too stiff, or this doesn't have enough topspin on the ball. And here is why I think that. What do you think? And this connection is something that's unique to us, and something that's unique to someone who plays the sport and does the engineering portion of it. And I think while what I feel is not to the level of a professional, what I feel with respect to an engineering problem is also a valued feedback that only comes from that engineering team that's working on this project all the time.
That makes a lot of sense. And I now wanted to touch on the simulation aspect of your project as well. Sometimes it can be difficult to balance, physical, like mechanical testing versus the simulation side, and maybe overvalue simulation compared to physical testing, or vice versa. So within your
Yeah.
project, to whatever extent you're comfortable, how are you able to kind of overcome that temptation and find the right balance between physical testing and simulation?
Yeah, definitely. We are in a software age, I will say. So it's so tempting for all of us, I'm sure we know it, to just whip out a laptop, stick some numbers in, and run a simulation. At least that's my temptation, because these tools are so advanced sometimes. But, and I mean, don't get me wrong, for, as I mentioned before, for rackets, for rockets, for airplanes, all of these things that require life or death levels of accuracy, and you can't iterate on these things, simulation will be central. Most of these will require simulation. But my opinion is, like, if you have a product like a tennis racket that's comparatively cheap to manufacture and to iterate on, it's always best to have physical tests more so than FEA, finite element analysis, see computational fluid dynamics, that kind of thing. All of these simulations tools that we are having, especially in the world of sports, where, as we keep going back to, feel is such a big thing. Simulation doesn't account for feel at all. And a lot of times composites come into play, for which is like the combination of multiple materials, each with their own specification. And many times the tools that we have don't aren't accurately able to simulate how these two different materials interact with each other, if that makes sense. Or if there are tools that can do that, it's a little too advanced and a little too expensive for companies to just use on a daily basis. So you can have coupon tests, but again, it's beneficial to have these physical tests of physical samples, because ultimately that's what the players and the consumers are going to be using. And as I keep iterating, if the material, even if it's the best, if the final product's the worst, it's the worst. In terms of for advice I have for school, it's good to have this knowledge of FEA, CF, frequency analysis, all of these simulation tools. Not to you don't need it to a deep extent, but you need a background on this, and you also need a background on this physical test, whether it's hardness test, compression test, tensile test, instron mechanical testing, frames, that kind of thing. It's good to have both to a breadth of ability, because it's important to know the strength and weaknesses of both of them, and to be able to understand when to use one, when to use the other, when to complement each other to get that best and most efficient design of a new product. Because I mean, you can't ignore the fact that you need to make samples to do physical tests, where simulation's a lot quicker many times. And it's a matter of, like, time is money, but also money is money. So just getting that, best, how do I say it,
The
balance of both of
balance.
worlds.
Yeah, for sure.
So I know that simulation, of course, physical is king, but I think like you were saying, simulations are useful to understand the relationship between how the material properties are and how it reacts. So from
Mm-hmm.
that point of view, are you able to have a deeper understanding through simulation to understand if I change the material properties of like UTS or max elongation or Young's modulus examples like that and get a different response in the racket? Is that valuable, or is it really just understanding how it will deform and wear under use that maybe you're not able to do in such a short period of testing?
Are we talking about simulation side, or like physical testing to get these Young's modulus values,
I'm talking about
elongation?
simulation. Like, is
Okay.
simulation valuable
Mhm.
to link material properties to actual like these words that you're using that's a feel like stiffness or push through, or is it useful for like accelerated wear that maybe you're not available to do for like years of hitting this back and forth?
Oh, that's a good point. Yeah, I think the values that we get from simulation are good because they give you a standard, if that makes sense. A lot of these values that FEA CFD provide for you are based on standards that ASTM provide for you, and a lot of the FEA mathematics is based off of that. So it's accurate to to a material science world, it's a very accurate tool. But as I said again, while these values can be taken into account for finding out trends for which materials are good or which materials are bad, they are many times not accurate to how the racket actually acts in real life. These rackets are so complicated and they are all sorts of geometries that FEA tools aren't able to encompass every single minute deformation that happens in the racket. So once again, simulation tools are very, very good, but sometimes physical testing, sometimes FEA provides, it won't break on this amount of load, but we do it on the court and it does break on that amount of load. And it's not a deficit of FEA or any of these simulation tools. It's simply that that world is not enough to support the sports engineering requirements. Obviously, metals, composites, very different. Metals are a lot more accurate in FEA, to my knowledge, obviously, because it's very much an isotropic material sometimes, whereas composites are not the case. And so just understanding how and when to use simulation, I think, is pretty key.
Definitely. Are there like regulations that you have to consider too in this like design and development process, like within your realm, like racket sports as well, like in terms of the materials you can and can't use? Like I think we talked about this a little bit in a previous episode centered around sports, but with like golf clubs, right? And so like
Okay.
that, there are certain materials where you could really launch a ball pretty far, but it could be
Yeah.
potentially banned by whatever agency or committee is deciding on the rules, right? So does that same principle apply within racket sports or no?
Within what I can share, there are things that some sports are more strict than others. And let me choose my words wisely here. There are there are certain specifications that you need to meet, and many times they don't tell you how to meet them. So it's very cool in that again, you're always pushing boundaries and regulation is key. I mean, if we drop racket sports for a second. I'm a big fan of Formula One. I don't know if you guys watch either of them, but easier for us to explain this because it's cars, and you can see that every single time a new part is added onto a Formula One vehicle, it's breaking a rule to an extent. It's pushing these boundaries, bending the rules. And so the same thing works in every single sports industry where there might be a certain regulation, but if there's a loophole like Formula One does, many times it's possible to create products within that realm and be able to eke out this new performance. And that might lead to rule change. It might just be cheating, or it might lead to it being accepted and then becoming a transcendent technology that becomes employed in all of competitors as well. And yeah, and Wilson as well, Adidas, Nike, I'm sure all of us do have that same mentality of pushing boundaries, trying to obviously staying within regulation, but trying to push regulation to allow us to provide more better products all the time.
Going back to your simulator, I'm really interested in where you perceive the difference in the data you collect from your custom built simulator to more of a traditional materials analytic equipment, and then where you can apply that data to create a faster product development cycle.
So Materials World has standards, ASTM. You want to use those when you are sharing information with other companies. So many times you get material specifications in the form of data sheets, material specs, right? And these all have these values that are all tested in that same way. So when you're taking in materials, you are looking at these values and you have these standards on which to go by. So in that case, you have more traditional materials analysis for us to use as our metric of understanding materials. And it's the same case the other way around when you want to share information with other companies, with other vendors, with other materials providers. Having a standard and using this global ASTM worldwide standard of material specification is very key and helps us eliminate the need to translate and explain every single time what you are measuring and how you measured it, for so on and so forth. But many times, as I said, these material specs, these coupon tests that they do aren't representative of the entire final product and how they react. So when it comes to understanding how a material reacts in product form, custom built testers are very, very important and many times help us gain a better gauge of what we need to know. And every company has their secret sauce that they don't really need to share with other companies. They just need to know internally. So a lot of the times, I'm sure with other companies as well, is there's custom testers that are important to gauge and understand and share only the best information within ourselves. And that sometimes ASTM and other testing standards don't really. And again, feel is something that's very, very key when it comes to that, because for sports equipment specifically, feel is king. If it feels good, it's winning. If it doesn't feel good, it's not winning. And ASTM doesn't, it feels not a criteria for them. So just being able to translate that and get the final product the best you can, custom testers are key.
Awesome. Awesome. So I kind of want to wrap up this episode with getting your perspective on the future of this intersection between the sports industry and engineering, and even, how physiology plays a role in all of that. We talked a lot about your racket engineering internship experience. You also have a passion for swimming as well. So just wanted to get your thoughts on maybe a particular sports innovation you're looking forward to, or that inspires you to want to contribute further in this field, whether it is rackets, swimming related, or anything
Yeah.
else that you've read about.
100%. I'd like to share about what actually got me interested in material science of sports in the first place. So as I told you, I did swim, and then I did a little bit of research. 2010, the Speedo Laser Racer came out. Now, this was a material that repelled water in ways that it didn't do. And this is important because when you're swimming through the water, you want to cut through the water as quick as you can, right? So when a water repels, it's able to translate and put you smoother through the water, and more so than skin would do. Now, this swimsuit was so good that year, 25 Olympic records were broken, and 92% of winners wore that suit. So basically, if you didn't wear that suit, you lost. So it was so good to the point where it got banned. It was deemed cheating to wear that suit. So that product was not produced at all. And at the time I was swimming, I wasn't a college student at all. Was profound to me that equipment could make such a big difference in performance to the point where it's called cheating. And so I think these new innovations, obviously working at Wilson as well, I've seen how much equipment can break rules, how much it can bring the human body up to new potentials. And these innovations like that I just showed you is something that helps me and keeps me wanting to contribute in this field. And material science is cool because, again, it's a growing field and many times it's still untapped. And our applications and our understanding and how we are going to use it is only going to grow. And being able to be a material scientist like we are opens up these doors. Obviously, we've talked a lot about sports, but this is the case for other industry as well. And, the doors are all open for us.
I love that. Thank you so much, Koki, for joining us today. It was a pleasure having you on the show and discussing your experiences and your kind of passion for the space. Yeah, it was just really fascinating stuff. So really grateful for you joining us.
Thank you so much for inviting me on. It was a lot of fun talking.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.